Hi class, today I'm going to be discussing the Bohr model and the Rydberg equation. So first let's discuss continuous versus line spectra. A continuous spectrum is colors sort of merged into each other as you see here. There's they kind of blend in certain spots. It's a rainbow of colors containing light of all wavelengths, but not all radiation sources produce a continuous spectrum. So let me explain what how this bottom part, these line spectra, occur. When a high voltage is applied to tubes that contain different gases, the gases emit different colors of light. When the light coming from those tubes is passed through a prism, only a few wavelengths are present in the spectra. Each colored line represents a light of one wavelength. A line spectra is a spectrum containing radiation of only specific wavelengths. So if we look here at hydrogen, we have 410, 434, 486, and 656. And each element has a unique line spectrum. So think of it as a fingerprint. So what happened here is that Johann Balmer, he was a Swiss teacher, determined that the four wavelengths, the ones specifically for hydrogen here, determined that the four wavelengths fit into a formula that relates the wavelengths to number values. So we could then determine what these wavelengths were. So Balmer's equation eventually was developed into the Rydberg equation, which is what you see here. And this is wavelength, 1 over wavelength. The RH stands for Rydberg equation. And then these are the different energy levels, 1 being the initial, 2 being the final. So we use this, we plug this in, and we can determine the spectral lines of hydrogen. So if you see here, this purple represents this one, this blue represents this one, this green, blue, turquoise, I'm going to say, represents this one, and red represents this one. So we could plug in the different energy levels that these electrons from the excited state down to whatever state it goes to, and we can determine what the wavelength can be for these. So here's the Rydberg constant. The energy absorbed or emitted from the process of electron promotion or demotion, basically excited energy states, can be calculated from this. So here is the constant, the Rydberg constant, and I is the initial energy level of the electron, and then N is the final energy of the electron. But before we tackle that, and we are going to tackle some problems with that so you can see how to calculate it, we need to discuss the Bohr model. So Bohr, Bohr was really interested in the line spectrum of hydrogen. However, when he looked at it, remember there's light as wave and light as particles. There's certain behaviors that just could not be explained. So he adopted Planck's assumption and went further with what he was seeing. So Bohr assumed that the laws of physics were inadequate in explaining what we were seeing or what he was seeing. That's where he decided to follow Planck's idea of quantized energy, this particles. So a charged particle moving in a circular path should continuously lose energy, and as the electron loses energy, it should spiral into the nucleus. But that didn't happen. Nothing like that was happening. So he pretty much disregarded classical physics and went on with Planck's and made assumptions about what he was seeing with the line spectra. So from his research, he came up with 3 postulates to basically from what he could see. And the first one is that electrons found at only specific distances from the nucleus in orbits. So only specific distances. Number 2 is electrons travel in circular paths in discrete energy levels. So pretty much like planets that revolve around the sun is what he was saying. And then the third, each element has a unique set of energy levels. Now the Bohr model is a big deal because this started research into this, and we were able to adapt. I say we, but through history, this was adapted. So he got some things right, and then we discovered that not everything worked with what he came up with. And one of the biggest things is that what he came up with only works for hydrogen. When we plug in any other numbers to try to determine wavelengths, they don't work. They only work for hydrogen. But that's okay. And in classical physics, again, wouldn't result in an electron falling into a positively charged nucleus. That did not happen. It wasn't happening, so he assumed that it would not. And circular motion is not wave-like in nature, so that there are certain things that were limitations to what he was presenting. However, there were 2 important points that we still keep in a current atomic model. So this has been updated from his, but he started this, and this allowed further research into going into it. So the two are electrons exist only in certain discrete energy levels. That is true. You cannot go outside of those discrete energy levels, much like walking on stairs. You can only end up on the top of the stairs and not in between them. And that's exactly what this means. And energy is energy involved in the transition of electron from one level to another. So these are the 2 points that were taken from his research. So we are now going to look at the Rydberg equation. Calculate the emission wavelength of the photon that is emitted when an electron in a hydrogen atom drops from the 4th energy level to the 3rd energy level. Is this photon in the visible region? So we want to take a look at the wavelength. That's what this answer should be in. And we're going to see, based on the electromagnetic spectrum, if it falls in the visible wavelength. So let's take a look at what we have here. So this falls from the 4th energy level to the 3rd energy level. So N1 is 3 and N2 is 4. So the higher one is here and the lower one is here. Okay, so, and then we're going to plug in with the Rydberg equation. So we have these are squared away. And once you plug this all in, it should end up in 1/meters because wavelength is in meters. So that makes sense. Now we're not done though, because this is still in 1/meters. So we need to be able to isolate the wavelength, the lambda of it. So which is what we do here. And this is the number, but we're not done because this is a question that wants to know if this photon is in the visible wavelength. So when we take a look, we're going to change it to nanometers so we can see, is it in the wavelength of 400 to 750, which is what would be here. And when we convert it, which is what's been done here, it's at 1875. So this is not in the wavelength of visible. So this is outside of it. It's in the infrared, which would be right here. And that's it. Thank you.